Welcome back to the present. Here we are on Articulate, and where are you? Look around, take in your surroundings, breathe, and be here with me. Okay, now you're here? Good. Welcome to Articulate with Steve McJones. This week I had my buddy Zach Schmitz, fun guy, very knowledgeable on the on the topic of his major, which was civil computer engineering. Civil engineering. I wonder if that's anyways, computer engineering, which not to be confused with computer science, even though they're just one word off, and it's not. Civil disobedience. Anyways, yeah, he was very knowledgeable, and it does kind of get really technical at the beginning, but you kind of need to understand a lot of those things to. I mean, that's just what, I mean, you're looking at your phone every day or your laptop every day and you don't even know what's inside of that bitch. And that's just how it just works for you. I don't know. And so to get into that, a lot of the technical stuff was really interesting for me, at least. And then, you know, as we get further into the episode, concepts become more abstract and a little bit less technical based. And, you know, we talk about AI and just where like innovation could lead potentially and things like that. So I don't know, it's pretty interesting. I had a good time recording it and I think you'll have a good time listening to it. So yeah, thanks for listening. I appreciate it. Hope you enjoy it.
So they're stuck back there. They're still probably they haven't got the news of Brexit yet.
Lucky them, right?
Right.
Righto. All right, back to it. So do people call you Schmitty or not? I'm sorry.
They call me Schmitz mainly. Schmitz. Or Zach.
Zach. Or my name.
You know, yeah, you can call me, my name. Yeah. Thank you.
Yeah, sure. All right, Zach, Mr. Schmidt. Well, so what are we here to talk about today? Is it your major? What is your major? Yeah,
so just kind of so my course of study is computer engineering.
Sure.
And so that kind of, I feel like a lot of people, when they hear that, they think computer science.
Right.
And so it does have a lot of computer science to, it is heavily involved with computer science. But I think the aspect that almost gets overlooked is the hardware factor of it, kind of. Because when you think of electrical engineering, you think of just like circuits and, I guess telecommunication and that kind of thing.
Sure.
And when you think of computer science, you think of like coding and like software design, that kind of thing.
Software versus hardware.
Right, exactly. Or like, I guess when I think of computer science, I think of just kind of like nerds at Google and stuff. Right. and then like, typing up the newest email thing or whatever edits they're making to their software.
Yeah.
But
so you do the coding or you do
the so hardware? that's the thing. It's ambiguous. And so it's like extremely overlapping. A lot of the classes that I have are focused on computer architecture. So maybe not necessarily the coding in terms of like a high level. And by high level, I mean close to human language and what we kind of see as user interfaces. Like with Google, you have your nav bar and your like search bar and all of your, add-ons and everything. What we kind of deal with is like the processes and instructions that run on your computer to execute that and, that kind of thing.
So a lot of it is user interface?
No. It is like ones and zeros, binary instructions.
Wow.
And
so do you know binary code?
Yeah,
Are you fluent in binary?
Well, so that's the thing. So being fluent in binary doesn't necessarily mean much because based on whatever instruction or protocol or thing you're doing, those ones and zeros mean different things.
Oh, really?
Yeah, so in terms of like English, like converting ones and zeros to language, it's typically in the form of ASCII characters. So each number in a byte, so a byte, meaning 8 bits.
8 bits.
A byte is 8 bits.
Wow.
Yeah.
We're really getting into it.
Right.
Okay.
And this is like pretty technical, but if you're like converting, just binary to English,
sure,
1 byte would equal 1 character. So in each like assortment or arrangement of bits between ones and zeros would be a different character. So I think.
So how many ones and zeros would it take to make like an A, for example?
So it's also a matter of the order. So binary is really kind of like a base 2 system where we typically think of numbers in base 10. So, you go 0, 1, 2, 3, all the way up to 9, and then once you hit 9, it rolls over to the next digit.
Okay.
So it's the same thing, but rather than going from 0 to 9, it goes 1 or 0 to 1, and then
resets.
And then it resets.
Wow.
And so, for example, the first bit would be 0 or 1. The second bit would be 2 or 0. So if it's a 0, then it's just not present. The third would be 4. The fourth would be 8. Yeah. So from there, you can use 8 bits to create 2 to the power, however, 2 to the power 8 minus 1.
Wow.
That's the max value.
Yeah.
So that would be 255. That's the max value of a byte.
And that's just within 1 byte.
That's within 1 byte. Whew. And typically what we're dealing with are, so it goes from byte, which is 8 bits,
right,
word, which is 32, and a half word is 16. So a word would be like just something very long, just a huge number. And now we're even getting into, like 64-bit numbers and whatnot, which are just even more enormous.
Megabytes? Where does that come in?
Oh, so megabytes and gigabytes, you typically view that in terms of like memory. Yeah, I feel like, it's within memory and storage. So memory being like random access memory. This is not going at all like where I actually intended it, or like,
it's okay. I mean,
which is fine. It's perfect.
We got time,
Right. But like memory and storage, you kind of think they're similar, but one is more for like long term. So on your computer, there's either a hard drive or an SSD, meaning solid state drive, which stores very securely meaning like non-volatile. It will not, like, if you turn off your computer right now, you're not going to lose like your operating system, which is stored on there. But and those are typically larger. So like, for example, on my computer, I have a 512 SSD, and an SSD is not a mechanical device, where an HDD or hard disk drive is a mechanical device where there's multiple disks, like physical disks, and it almost, there's also a arm that almost acts exactly like a record player or something. Oh, wow. And it just, the disks spin mechanically, and where the arm is over it reads that data, being like,
and that's what like the fan in the computer is,
No.
Not the fan, but that's what you hear, right?
So it depends on the type of computer. So like, for example, since mine is SSD,
yours is real quiet compared to mine.
Since mine has an SSD, it is not that. Like, it is all digital logic. There's no mechanical spinning disks or anything. Right. And so for that reason, SSDs are a lot faster and, more expensive.
Right. And that comes with, technology progressing to making things smaller, basically.
Right, exactly. Yeah, they're much more compact as well.
Yeah.
But like, I remember when I was in high school and stuff, I would always, build my dream PC online, like put it all in the cart and stuff. But obviously I can't fucking afford that shit. But like, like a 1 terabyte SSD would be like $400, and you could get a similar sized hard disk drive for like maybe 100, so cheap. And, it was just that boost in performance that you see and whatnot. Yeah. And you're like, oh my God, it takes like 5 seconds to boot up my operating system rather than fucking like 30 seconds. And you're like, okay, whatever.
Yeah, it doesn't matter that much.
Right. But
I get what you're saying.
So that's storage. Sure. And when you hear memory, I feel like, at least when I was learning stuff, it was kind of like
storage and memory.
They seem like very similar, and they are. But I guess it's almost the next level up in the hierarchy. Really? So there's multiple levels of memory, and so it's almost a pyramid.
So it sounds like storage is a place where you just put things, whereas memory is re-accessing, or
yeah, it's almost, so the idea is that on your processor, where you're...
This metaphorical processor. The hyperbolic processor.
Right. But on your computer's processor, you just want it to run through instructions, which are in the form of ones and zeros, as fast as possible.
Sure.
And so just like how in real life, an assembly line has to execute quickly, if your resource or, whatever you're using is super far away, like, for example, in your memory or, across the room, it's going to take a lot longer and you'll be bottlenecked by you waiting for the instruction to execute, or like you're waiting for somebody to deliver that object for you to like turn into a toy or, go down the assembly line or whatever.
Right. And
so the idea is that you want to move all of this memory up this pyramid of knowledge, or like of memory in storage. So at the base is your mass storage. That's where your hard drive and your SSDs live, where it's non-volatile. It's going to be there. If you turn off your computer abruptly or if it crashes or anything, it's going to be stored.
Is it still software?
This is all... Okay,
This is all within the software realm.
No. This is where the software and hardware meet.
That's okay. That's what I was thinking. That's kind of what it sounds like.
Yeah, exactly. And so this is kind of like when I say computer engineering, people are kind of like, oh, so like computer science, just because it's like one word off.
Right.
And they're like engineering, science, same thing.
Right.
And so like this is where, computer scientists don't necessarily have to think about this because it's abstracted away.
Sure.
So, like, based on operating systems, and like that's kind of a generalization because obviously computer scientists who work at the lower level, like with driver programming or operating system programming, have to know this stuff.
Okay.
They have to understand instructions and opcode to a degree and the architecture at which their operating system is running on. But for the typical computer scientist, which is just, somebody that's like running and like building a website, you don't necessarily have to understand all this.
Sure. So back to the pyramid.
Oh, so this pyramid this is kind of like just how I learned the structure of memory and like positioning.
Right.
So
SSD
and hard drive at the base, and then you have your RAM. So.
All right. Sorry about that. I think we are good.
Yeah. Okay.
So the RAM, right?
Yeah. So you have your base SSD, then RAM. This is just kind of like where when your computer's booting up any process or program, including your operating system.
Copy paste, but not really.
Kind of. It pulls it up into your RAM, fills it up, which is typically around 4 to 16 to 32 bits now, or bytes now. No, gigabytes now.
Oh wow.
Yeah. So where your memory is like your main memory is like 256 gigabytes to like multiple terabytes.
And then so, as it gets closer to the top, it's closer to the processor.
Exactly.
Right.
And so after RAM, it gets moved into your caches, which typically now there's 3.
I thought those were stored on like websites.
Cache?
Yeah.
Oh, so it's like very similar in the sense, and they act very similarly, where it's just information that you have used recently or are neighbored physically in memory or something that you need to access quickly and constantly.
Sure.
So, like something that you might want to keep cached, like if you're running a program or like a game or something, you're probably going to need like to cache a bunch of like information like where your player is or, what your player has in their inventory, so that way you don't have to constantly pull that information back up from the main memory, which can take thousands of cycles.
Yeah.
Cycles meaning every processor is given like a clock rate, which now is from like maybe 3 to, or like 2 point something to 4 gigahertz. So really fast.
Yeah.
But still.
So really fast.
Right. So really fast, but still like 1,000 cycles to a few thousand cycles that can slow down your program by a decent amount if you're doing it frequently. Right. So like, yeah, it's fast, but we still see lag. Like, and you're like, how do we see lag if this thing is going so fast?
Yeah.
And you're like, well, just cause. but yeah, so basically the more constant you're like accessing this memory, the more likely it is to be closer to the processor, which, you know, it'll go from your L3 cache to your L2 cache to your L1 cache. And there's all types of different architectures that are designed to, you know, whether it's like first in, first out, because those caches get smaller and smaller and they're even faster to access.
You guys use a FIFO system too? First in, first out?
It depends, you know.
We just do that in hospitality to get food out. Like,
first that makes sense. First out, yeah, but there's like a ton of different like, you know, structures that you could implement. You know, like first in, first out, it might be easy to implement, but you don't necessarily know if that has the best performance because, you know, maybe you're constantly kicking out like something that you want and keep requesting. Right. So sometimes
that's like, you know, with the croutons, I'm not always going to get the bottom of the croutons and put them on top. Sometimes I'm just going to fill that thing with croutons again, and, you know, so this is the fastest, easiest way to do it because...
Right. Sure.
Because, yeah, it's not like that. But no, I get it. It's more complicated than
It's
first in, first out.
Right. And so like
based on performance.
Right. Exactly.
Using the metric of performance.
And so like that's exactly the goal, I guess. You want this thing to perform as quickly as possible. Yeah. That is the goal.
Sure.
And so
is that going to go into the history at all?
So history, yeah. We can go back to history. We just kind of like went on this.
Yeah, no, and it was good. I liked that little. That's, you know, fundamentals of like kind of what you do a little bit. You know what I mean? Right. So it's like, so now we have that basis understanding, and now we can continue on to you know, other things.
Yeah. So I guess the history, I honestly like, because like it's kind of ambiguous to me in many ways because I don't like, you know, I'm learning about the computer science and like the architecture and everything about that. Yeah. The history is kind of like an afterthought. Yeah. Because it's just moving so fast. Looking back is like, it's important sometimes, but like, you know, we're not using vacuum tubes or any of that shit anymore. Right. So like back in the day when computers were like enormous, taking up full rooms and whatnot, the technology was like vacuum tubes and stuff. And so like a tube would break and you would basically have to figure out which one it was and like replace it and stuff. And that's how you created logic. So those were kind of like, this is where I'm like iffy on it because, you know, that stuff hasn't been used for like decades. For sure. And so from there, you know, that was like with IBM and I think Bell Labs and whatnot, maybe. But in, probably the 60s or 50s or something, in Bell Labs, which is now AT&T, scientists created the first transistor, which is a circuit component that has three ports basically. And so the idea is that these transistors could facilitate computer or just like logic in general. And they were a lot smaller, affordable because they're made out of silicon. Right. And I think originally they used germanium as well. But
what does logic mean?
Logic meaning like almost philosophical.
That's because I'm looking into philosophical logic. I know.
Right, it's exactly that. Like really? Statements. It
does that within computers somehow?
Exactly. Okay. It does that, but rather than you saying like if this then that, rather it's all within the context of like comparison or mathematics. Okay. In the sense like for a computer would argue or like logically say like if this number is bigger than this, then do this. Okay. Something along those
that's kind of, and this is going to sound really like novice and dumb, but like kind of like Excel, there's some formulas where it's like...
Right, yeah, it's exactly that.
Yeah, okay.
Or like an and, like these two, if this and that, in the... like
given this context or whatever.
Right. And so like the truth table for an and operator would be them both being true, and if this and this are true, then the statement is true. Right. But if this and that, and like one of them is false, then the whole statement's false. Right. Because...
invalid.
Yeah, or invalid, or what... typically you think of it as like 1 being true and 0 is false, and like you think of a true-false kind of operation. Sure. Or you could say invalid or valid. Right. I forgot what I was saying.
Just the history of...
So these transistors were created, and they're pretty cool. Silicon is abundant.
They do logic, apparently.
Right.
They're contemplating life and death at this point.
Right, exactly. Like, these things have a mind of their own.
Right.
But, like, they are able to create logic gates, meaning, like, these fundamental computer components that, without them, we wouldn't be able to, have what we have today. So, like, those components are like an AND gate or an OR gate or a NOT gate.
And
so,
those
like,
are the first to do
those are the foundation of everything. Wow. Like, to have a computer, you need, like, just strung together millions of ands, ors, logical operators.
Wow.
And it's crazy, like, to think, like,
somebody wrote all that code.
Right. And it's not even like writing, like, physically put it together.
Yeah.
Like, and so that's the thing. Like, right now, people aren't, like, physically putting them together. Like, they have machines that mill wafers and everything and do all this other stuff.
They have machines that make machines?
Basically. Yeah, but I don't know. It's pretty interesting. And so I guess...
Where did it progress upon that after that? So that's the foundation. And so how did they progress upon that to get those? Because the first you said only had 3 or something like that.
Oh, no. So 3 as in, like, 3 ports. Like, there's, like, the gate, base, and emitter. So those are just, like, I don't know, have you ever seen, like, an LED, a light bulb? Like, there's a positive and a negative end.
Right.
These have, like, rather than just, like, having, like, a positive and a negative end, they have 3 ports, and, like, if you apply a voltage to one side, then,
it passes.
It lets a different signal pass through it.
Oh.
And so, like, that's where the logic comes in. It's like, if this port, is high, then this one is also high. And,
okay.
Or, it's whatever.
Sure. It's whatever you make it to be.
Right. And so this is, like, pretty abstract and kind of confusing if you don't know, like, the dynamics or, like, the diagram of a transistor. But, it gets super physicsy too, which is kind of cool because, like, I was in class and my professor was talking. He's my electronics professor, and so we're learning. Like, I'm actually currently learning about, like, the molecular design and, like, understanding of these types of circuit components, like diodes and transistors and MOSFETs and all that stuff. And so I don't know if you want to go into the, like, actual, like, physical chemical construction of one, but that's pretty cool too.
Yeah. If you want to dive in.
I think it's kind of, like, too
far off.
Too far from, like, the computer-y, like, stuff that people want to hear about, probably. They're like, okay, nerd. But yeah, eventually, so, like, basically, with these new components, they are able to string them along to create, like, more and more complicated ones.
Sure.
So, like,
we're to the point where you get the millions and millions.
Right, exactly. And so, like, from AND gates and OR gates, you can, and NOT gates and whatnot, not meaning, like, if you put in
anti-gates.
Right.
It's the shadow gate.
It inverts the operation that goes into it. So, like, let's say it's a 1, inverts means the output is a 0. Mm-hmm. In OR gate, in, like, philosophical logic, and this logic is, if either one of the inputs is true, then the output is true. Mm-hmm. So the idea is that these I forget what I was calling them. They're called gates.
Right. Yeah.
But, like, the
mega gates.
Yeah, the gates. Yeah. But, like, an AND gate could have 2 or more inputs, and if 2 of them, like, if they're both true, like 1 and 1, then the output is also true. So, like, for me, like, it sounds very clear, and it's just because I've been so, like, enveloped and consumed by it. Right.
For me, it's
right. And I think, like, maybe if people have, like, a philosophical background, they can definitely, like, understand the logic behind it.
Sure.
And it is very, philosophical logic. It's based on it. Mm-hmm. But anyway, so from there.
So are computers? Do they have, like, a way of processing things that is logical, like that, like, philosophically logical, like, getting into, I don't know, I think you said you were going to talk about AI a little bit. Does that play a big part in where computers are progressing?
So I feel like a lot of these, like, instructions, the like ones and zeros and like these gates and stuff, it's so abstracted right now because, I mean, to have to think at such a microscopic level, like just when creating like like a program that is like a calculator or anything like that, it would be extremely inefficient and tedious. So like that's why for the most part, I don't know if this is answering your question or
I'm following.
So now rather than like worrying about like all these gates and stuff, you can almost you can just like have variables and functions.
So that's kind of where you were going. We're going through the history up to where we are now. So,
right.
So where we stopped? We stopped with the invention of those three.
The transistors.
The transistors.
Yeah.
Yes.
So yeah, that's
where we are.
That's kind of where we are.
Really.
And yeah. And I feel like I said this earlier, but you can like build more and more complex things like multiplexers and decoders and encoders and ALUs, and that's a bunch of jargon. But look those up if you're interested.
Sure.
And from there, like this is like a big jump because it's like, you know.
Well, we covered the topic for sure.
Right.
At least
within
that. Yeah.
And so now you have a processor. Now you have
we have a processor.
Now you have a processor. You have memory. You have like a weird spinning disk thing. You have floppy disks and all that shit.
Yeah.
So now I kind of wanted to talk about operating systems for a little.
Sure.
Because they're kind of
the basis of
fun.
the pyramid.
Yeah.
Yes.
Yeah. And so like operating systems are kind of like the things that sit right on top of that hardware and make it software.
Yeah.
So
the line.
Basically, like an operating system deals with the instructions and whatnot that you would typically see on your computer, and it. Oh god, that was a bad explanation. Anyway, so like it deals a lot with.
Well, OS system, right? The basis of an OS system is, you know, what your computer looks like when it starts, and
but that's not true.
It's not.
No, so like your operating systems, like or your computer's like display, like what it looks like is like a program running on your computer.
Okay.
So like for example, you can download a different appearance on your computer.
Right.
And like,
but that's not a different OS system.
That's not, and therefore, yeah, it has nothing to do with your operating system.
Okay.
It's just like a different program. So your operating system facilitates and schedules when programs run, how long they can run, what memory or addresses a certain program can access, permissions.
So like within the context of say like a phone, you know how we have like iOSs, right?
Right.
So and those get updates all the time. So you know each of those updates, like you said, it allows certain things to run longer or start up quicker, or you know, has different processes within it, right?
So, sorry, on operating systems, there's a program itself, because it's all a program in general, called like a scheduler that kind of like facilitates those like context switching between processes.
Okay.
And so like a program and a process are different in a sense that like a program is like a static thing and a process is like a running program.
Sure.
And you can switch between them. But
yeah,
so like,
so how are you trying to, so the point, you know, you can take your time and we'll get there, right. But the point is to articulate what an operating system is, because that's what you want to talk about, right?
Right. So it just kind of like, the thing is, it's just like so all encompassing.
Sure.
And to like define it in kind of like a few things.
Yeah. Well,
without being like super technical.
Yeah.
And I guess you could just like Google a definition.
Yeah.
But like, I don't think
I think it sounds pretty interesting. Like I want to know now that we've talked about it a little bit.
Right.
I'm interested.
It's I feel like what I was saying earlier kind of, I think it does it justice. It kind of facilitates the layer between hardware and software, where like it takes those instructions.
Oh, okay. I'm not with it now, but I get where you're going now. Like it turns physical reality into the software.
Kind of.
Right.
Like in the sense that when you're typing on your computer and whatnot, your operating system is taking that device, which is like your keyboard, taking the messages that it is receiving from that, using the driver that keyboard is running on, meaning just like a set of instructions and like program that is like, all right, this is the language that this keyboard is using. Taking that, interpreting it, putting it into, you know, like a document or whatever you're typing it in.
So like the brain a little bit?
It is like the brain, but I feel like it's, I don't know. I feel like a brain would probably be a good way to put it.
Okay.
Just because it just does so much.
Right. I'm sorry I'm so simple-minded about
No.
Like, I wish... I'm trying to... Yeah.
It's fine. Like the thing is, I feel like we've talked about a lot of things, and this is like multiple years of my education. So it's really hard to kind of like just compartmentalize them in a way that's like generally understandable. Like, right. Yeah. Especially because, you know, going from ones and zeros to like AI, that's big, you know?
That's
like,
huge.
And I mean, if it was very simple or I guess easy to kind of like see that jump, you know, like back in the 70s, we would have been there, you know? Yeah. Like, but in that, hence like now is when like AI is really like flourishing and whatnot. Yeah. But I guess... Yeah.
Well, do you want to talk about AI a little bit then? So how is AI flourishing right now? What is happening within the modern technology world to the point where... You know,
so it's just capable... Like, so currently, the reason
when did AI even start? Do you know?
So AI theoretically has been around for a long, long time. Like Alan Turing has been like noted the like father of modern AI and artificial intelligence and everything. Sure. So like he has, and many other people have... you know, created a lot of theoretical things that are fundamental in the field of AI and whatnot.
True. And,
you know, he was kind of a pioneer because it wasn't necessarily like possible at that point. You know, there weren't like modern computers to actually do it.
When was this again?
He was alive during like the World War II and whatnot.
Oh, okay.
So, you know, it wasn't, and he created the Enigma machine to decode the thing for the Nazi codes and shit.
Oh, there's a movie about that.
Exactly.
With Benedict Cumberbatch, right?
Exactly. And so, yeah. But currently, the reason that AI has been flourishing so much is because, first off, we have the computational power. Like, there's servers that are huge. They're running extremely quickly. And we have the data. Sure. Data is really, like, the keynote of why AI is, like, flourishing.
Really?
Yeah. So it's almost like teaching itself, like based on a bunch of like information, and it's just running these test cases. And so
it's like, does it use like the scientific method to run those cases?
No, it's basically just like imagine like this simple,
like a simulation,
like a game, yeah. or anything. And so like once you die, you know
you realize why you died,
or it doesn't necessarily realize, which is kind of weird. It just like realizes, okay, this time I lasted longer, so my score was higher, so it quantifies it. And so that's the kind of like, I guess some of the tricky part, quantifying like success. But with data you can say like this is success, I guess. So for like facial recognition, like an AI network would basically have like thousands of pictures or something. It doesn't matter like what the picture is, as long as it's like a consistent picture of like a person or, you know, something that it's trying to identify. And so at first you're like saying to you're writing your code and you're saying like, all right, is this a human? Or like, is this whatever it is, like a dog or a door or stairs?
Recognizing objects.
Right, exactly. And so the first time, it's probably going to basically randomly guess almost. It's going to be like, no, yes, yes, no. And it's like going to be very wrong. But then, after it compiles all of those results, it says it does a different generation, basically. And based on different algorithms of like learning, which I think they're called like gradient algorithms, they move closer and closer to like a correct, accurate answer.
Accuracy.
So they basically say like, oh, these like, and the thing is like a lot of times the people that design these algorithms, they know the goal and they know kind of how it's being done, but they don't know the process. Like it's so hard to quantify and like understand what the computer is doing to learn. And it's just ridiculous because these things are literally learning and have minds of their own.
By themselves, yeah.
Right. But I guess the thing that we control is the goal state. Mm-hmm. Like if we say, and getting into like...
Is that like limiting the AI? Is that what the goal state is? Or what is the goal state?
The goal state is basically saying, it's like the cookie that you give something when it, like your dog when it's doing good. Right. Or like the toy you give your kid when they're behaving well or something. Sure. It's like once they perform well, mm-hmm. you give them that that goal state. And it says, and obviously your computer is not looking for a cookie or anything. It's looking for what you tell it to look for. Right. Which is that goal. Okay. And so
once it achieves the goal, you let it know that it achieves its goal, and then it can shut down.
Yeah. and so theoretically, like once you tell it's like, oh, what you've been doing recently, like with this iteration, it has been reaching the goal state more. So whatever the trends that you have like done from this generation from the previous mm-hmm. have been in a correct direction. Okay. By this amount.
So it's narrowing down the precision now.
Right, exactly.
It was accurate in a lot of cases. It's right. Like looking at the precision now.
Right.
Interesting.
And so and this will take forever. Or not forever.
Because is there like the perfect, like can it achieve perfect yet?
I don't. Well, I mean, just like anything is never perfect. I don't.
Right.
Think.
That's what I'm thinking.
I don't think anything like any algorithm or anything is ever going to 100% identify every case mm-hmm. because I mean even as a human like you can't. Right. But these probably can identify better than humans, like at least objects and stuff. Mm-hmm. Which is crazy. So
what does that look like moving forward?
So I mean currently it's kind of it's ridiculous. Like it's crazy because there's so much data. Right. Like it's not just predicting like or seeing an object and saying like, oh, that's a chair anymore. Mm-hmm. It's like, what does this person want? Like, what is this?
Damn. It's like trying to be proactive as opposed to reactive.
And that's the thing. Like, since the goal state is, and like this is all in the context of like big tech business. Mm-hmm. Like with Amazon and stuff, they have like, here is your profile. This is your, this is your online presence. And so like big tech companies have like profiles of you, and the AI, its job is to get you to buy more things, or at least put that stuff in front of you that you engage with.
Right. More clicks.
Yeah. And it's not necessarily more clicks, but it's more like present time. Okay. So it's like the longer you stay at something, that's what they're looking for.
Okay. So your attention.
Yeah. Which is crazy.
That is crazy.
And watch The Social Dilemma. It's kind of all about that.
Yeah, I watched a little bit of that.
Yeah, it's pretty cool. And kind of fucked up.
The narrative parts of that story were kind of bad, though. The family.
Oh, yeah, that was so cheesy.
It was really funny, though.
Right.
But yeah, no, that's crazy. So moving forward, is AI just going to run shit?
I don't know, like self-driving cars.
They seem to
automating.
Like you were talking about, the phone, looking at your face and identifying it, facial recognition.
Right. But that's already pretty good, I guess. I think I wouldn't say like obviously as you said, it's like not perfect, but like it's pretty good. And I guess like I don't want to say that's in the past mm-hmm. or not where it's headed because obviously facial recognition and object recognition is also.
I think what is it going to do after it has perfected that or reached the goal state?
Right. Or like 99.99% accuracy mm-hmm. or something. And I guess the next thing is kind of probably going to be I don't know. It's the crazy part. Like, like self-driving cars. Like, I feel like that's
probably going to be putting like cameras in everywhere that AI can access like all the public spaces. So that way it knows it can, it can attempt to, I think there's a movie about that with Tom Cruise where it tries to, it predicts crime and stuff like that. And,
Yeah, I guess that could be like a network or, something that could happen.
Well, and cars are doing it now, like predicting crashes and being able to like stop. There's
like if they're yeah. I for some reason predicting crashes, I was like, what? But yeah, no, it goes auto. In a way,
maybe it will get to that at some point where it does actually predict crashes.
Which I guess it makes sense. Like they have lane like they have
stay in the lane.
Yeah, they have like signals and sensors that are like beep beep beep, you're leaving your lane, or like a lot of them they won't let you veer out of your lane unless you like do a an actual like kind of aggressive turning.
Yeah.
Like if you just kind of like let your hands like slightly go, they don't necessarily turn.
Right.
Like I mean, obviously Tesla is like pretty cutting edge, but that kind of stuff.
No, yeah. I actually had a friend who was on a few episodes ago. That's like he went to UNOH for like technical degree. It was like 2 years, but he was super into all the AI and stuff like that. And he was talking about how cars, there was a lot of change, and now like all the little changes that they're implementing is just like more AI based.
Yeah,
which is really cool.
Yeah, so that kind of goes into the other topic I wanted to talk about, like the Internet of Things in general.
Oh yeah, the Internet of Things.
Right. It sounds kind of cheesy, but it's pretty cool, I guess. I would say a little needless sometimes, but like basically, so like within a car system, there's thousands of little microprocessors and microcontrollers and sensors and stuff now. So similar to your car, there are those sensors in like just everyday technology, just like microwaves, ovens, your refrigerator, and all that stuff. And like there's if you're buying kind of newer technology, there's like apps probably that you can have that connect to your Wi-Fi, and you can control something like an alarm system or something from like a remote place, like your work or office. And like there was this funny thing that I saw where you could literally it was like a cocktail mixer maker or something, and you could literally just like you're at work, you say like, all right, make this, and then when you get home there's just like a cocktail like ready for you.
That's crazy.
Right. And so it's like stuff like that where it's small, compact, or maybe not small, compact, but normal everyday appliances that have pretty intelligent hardware, computers, and whatnot within them.
Yeah.
So that's kind of like what that is. Like the Internet of Things. Basically, like everything you own has a fucking like internet presence right now.
Yeah.
Like, and yeah, it's kind of weird.
Yeah, no, it's crazy. That's what I'm saying. The world's just gonna start running itself. There's this poem that I read like sophomore year. I think it was a poem or like a short story.
It's called There Will Come Soft Rains.
And it was just about a self-operating house
By Ray Bradbury.
that was in the future, and it was like the last house that was alive, and it was just these like little fake mice running around, and like toast was ready in the morning, but nobody was there to get it, and like the clocks would run, and like the garage would close up at a certain time and everything. Right. And then eventually just one thing like happened from the outside, like a tree fell over, and then the whole system just came crashing down, and it was really sad and melancholy, but also very realistic.
Yeah.
And it's interesting to see how we would progress towards that. But
right.
I guess that's where we're headed, yo.
Right. I mean, to a degree, yeah.
And then we'll just become, the people in WALL-E that are just fat, looking at screens all day, floating around.
I kind of, I know I'm kind of optimistic in the sense it's like...
Yeah, so I'm very pessimistic, sorry.
And like, I could see a ton of people just like putting on weight and getting really lazy as soon as like robots take care of us, and like they don't need to work or anything.
Right.
But I feel like it almost gives people more time to experience real life. Like the reason that these technologies are getting built and whatnot is so that your life is convenient. Mm-hmm. So you don't have to worry about like...
Yeah,
maybe the cocktail example is a little luxurious.
Yeah.
But like,
you don't have to worry about spending time doing that. So
right.
Then you can just start drinking.
Right. You can just be an alcoholic. Yeah. But I guess like it's supposed to streamline the stuff in your day that you don't. Yeah, it's to streamline the stuff you don't want to do so you can get to the stuff that you want to do.
Right.
And so just like I guess manufacturing jobs, a lot are being taken over by like these assembly lines that are almost entirely run by robotics, that which in the short term is obviously not great because a lot of people get laid off.
Right.
But eventually, you hope that those people find new jobs
or we find a new system.
Or a new system that can support those people.
And we talked about that in Porch Time, which is a really good episode, by the way. Self-plug, right? But we actually talked about, it's just an episode with some of the boys out on Porch Time. But the episode's called Porch Time. But he talked about like a universal healthcare system and like a universal basic income type stuff.
Right. And so the, idea is, if we do get to a point where universal income, where you can have like a life that you don't necessarily need to do these menial labor like works, you can have that time.
Yeah, that'd be so cool.
Right.
Oh man, so that is exciting. We get to do what we want hopefully someday in the near future, or we die. Either way.
Right. And I feel like I guess the fear of it taking our jobs is going to hold us back.
Took our job.
Right.
You ever watch South Park?
Yeah.
Okay. Cool.
Yeah.
That wasn't just out of nowhere. Awesome, man. Well, I think we covered a lot of topics here, and finished on hopefully a more optimistic note there at the end.
Yeah.
Do you have anything you want to plug right now?
Anything I want to plug?
Yeah.
No, I don't really have anything besides like classes and like my job working.
Yeah, fair enough. But if this interested you at all and you listen to this, do you think this is what makes you want to do this?
Oh, it's just like really cool. I don't know. Like it's just really freaking cool. Like there's always something different. There's always something moving. Yeah. There's like an art to it as well. Like specifically the computer architecture and design stuff, which I'm doing research and whatnot with.
Sure.
There is an art to it, and it's elegant a lot of the times.
Wow.
It's very it's not simple, but it's really complex. But that's kind of when things line up. Yeah. It just seems like
you're like, wow.
That is a very well functioning. Like it's almost. Yeah, I feel like those 3D videos that you watch when you're a kid that were like maybe in like music class, and it was like super elaborate, like these robotic looking things that were playing like this crazy song. Yeah. I don't know, they were like animations.
Sure.
It's almost like that. Like there's just like a bunch of fucking marbles flying all over the place and like dominoes flipping everywhere, and you're like, how does this sound like this? It looks like utter chaos.
Yeah.
And you're like, all these like weird things flying across the screen, and you're like, oh.
It's just beautiful.
Right.
Wow. That's awesome, man. All right. Well, I appreciate you coming out and talking about it and being informative and whatnot. I learned a lot of it.
Yeah, I hope I wasn't like way too confusing at the beginning. I probably was.
No, I mean, I was able to follow. So are you here? Did you enjoy it? Are you present? Are you thinking about your future? Are you thinking about your phone? Are you thinking about your computer? Are you thinking about the way that my voice somehow creates vibrations through a freaking microphone, travels through a wire, into the computer, up into the air, into your phone, into your ears? How does that work? I don't know. It's amazing. It's crazy. It's cool stuff. But I'm glad it happens because I love to be the center of attention. But also, I love to learn things and teach other people things and learn things with other people and be taught things. And, that's life. The song by Frank Sinatra. Anyways, appreciate it. Thanks for listening. I love you, amen. Okay, bye. Doug Dimmadome, owner of the
Dimsdale Dimmadome.
Yeah.
Hey.
All right. The Zach and Cody episode where they're doing the High School Musical within the episode, and Ashley Tisdale's actually in it, and she's like, I should go for Sharpay, and they're like, no, you wouldn't be a good Sharpay.
Oh my god!
And they do the mock, brr, brr, they do it backwards. Yep. I don't know. Cool. There we go.
There we go, mate.
We fucking got it now. When did it start cutting out last time? I think it started cutting out about 26 seconds in. It looks like.
Righto.
What? I think doing accents is more about knowing what the people of that dialect say and knowing their phrases.
Right, like the slang or just kind of like vernacular.
Right. Okay. We may still have mail.